In our first lecture, we talked about the notion of a system, and according to our definition, okay, so let's quickly remember what we saw. According to our definition, a system, or what we mean by a system, is a differential equation, basically. Okay, x dot equals f of t x u. Okay, x is a vector, u is a vector, and t is the time. Sometimes this differential equation is accompanied by an algebraic equation, which is called the output equation, or sometimes the measurement equation. Okay, y equals h t x u. So this is the most general form of how a system looks like. Okay. Now, x is a vector in Rn, and this number here, n, is what we call the order of the system. Okay, so this is the state. And here u, which again is a vector of dimension something, let's call that something p, is what we call the input. Things that we use to manipulate the evolution of the solution of this system x of t, and y is another vector q, which we call the output. Okay, so these are sometimes, from this system we cannot read, we cannot measure every single state variable, every n of n number. Okay, so from that n number, suppose that we can only measure just a subset of them, and then that subset is indicated by the output. Okay, and t is time. Okay, this is called a continuous time system, which this course will be mainly about. Toward the very end, if we have some time left, we'll also be talking about, very briefly, discrete time systems. Okay, but for now, for quite a long while, we will be interested in this continuous time differential equation or continuous time system. Okay, now this is the most general form of what we mean by a system, and for a while we will not be considering this, but we'll consider it a subclass of this definition, namely an autonomous system. Okay, and by an autonomous system, we mean that the evolution does not depend on the input. Okay, and the right-hand side, this function f, does not depend explicitly on time. If that is the case, then the system simply becomes x equals f of x, and such system we call an autonomous system. Okay, autonomous system reads x that equals f of x. Okay, the difference between this and that is the following. To be able to figure out the solution x of t for future time, you need three pieces of information. One of them is the initial condition, x at initial time. The other is the input signal that will be affecting the system for the future, and also the initial time, t. But for this simpler case, all you need to be able to determine the future of the system is the initial condition, x at some initial time. And without loss of generality, you can always take that initial time, because the right-hand side doesn't depend on time, that time to be 0. Okay. Okay, so that's an autonomous system, and associated with an autonomous system, there is a very important solution, and that solution is the following. It's called the equilibrium solution, let's say. Okay, so that is, it's a constant solution. If you start at that point, and if you stay at that point for all future time, that point in space Rn is called an equilibrium point, and that we define as follows: equilibrium point or points. Okay, an autonomous system may have just a single equilibrium point, may have more than one equilibrium points, it may have no equilibrium point. Okay, anything is possible with nonlinear right-hand side. So the definition of an equilibrium point such that f(x) eq satisfies this equation. Okay, f(x)q equals 0. Now, of course, x is a vector in Rn. Since f describes right-hand side, it also produces a vector in Rn. So that means this 0 is the 0 vector in Rn. Now, if that equation has a solution, xeq, okay, that point in Rn we call an equilibrium point. Okay. Note that if you start your system from the equilibrium point, we're talking about autonomous system now, therefore all you need to be able to determine the future of the system is the initial condition. If you start your system from the initial condition, xeq, such that this vector satisfies that equation, then it's clear that you will stay at that point for all future times. Okay? Because plugging f of x, xeq here, you obtain 0. So x that equals 0 means that x is not changing. Okay? And it will not be changing for all future times. It will always be staying at xeq. Therefore, for this initial condition, x of t, which is how we denote the solution. Solution remains at xeq for all future times. Okay. And then, to exemplify this setup, we talked about probably the most famous example, nonlinear example, from the physical world, namely pendulum. Okay, so let's quickly remember that example, and today we'll see two further examples, okay, for a system. We discussed pendulum with friction. So this is a rough picture of the actual physical system. The pivot here, and this guy can move back and forth about the pivot. Okay, this is the vertical line. This is the direction of gravity, G. Here the mass, let's say, is M, and this rigid rod is of length L, which we assume to be massless. Okay, and then this system has the dynamics. As such. Okay. Now the dynamics of pendulum with friction can easily be obtained, and it's ml theta double dot plus mg sine theta plus kl theta dot equals 0, where theta is the angular displacement from the vertical reference line. Okay, and all the others, m is all the other things are constants. M is the mass, L is the length, G is the gravitational constant, and K is a constant that describes velocity. Okay. Now, this is a description, a valid description of this physical system, but it doesn't fit into our description of a system, but that's a minor difficulty. We can easily put, once the dynamics are given, we can put those dynamics into the form that we will be working with. That is the form of x that equals f of x. For that, what we do is we choose a state, and usually if you have a physical system, you go with the physically meaningful variables. In this case, it's obvious that there are two physically meaningful variables. One of them is theta, the other is theta, namely the angular velocity. Okay. With that choice of state, x1, x2, chosen as such. x1 is now the angle, x2 is the angular velocity. We obtained, or we have been able to put the dynamics or re-express the dynamics in x that equals f of x form. Namely, we have x1 dot x2 dot equals x2. We have minus g over l sine x1 minus k over n x2. Okay, so this is what we call the derivative of the state with respect to time. This is x dot, and what appears here is our right hand side, okay, f of x. And for this system, there are a bunch of equilibrium points, that is, points that satisfy f of x equals 0. If you equate the right hand side, f here, to 0 vector, 0, 0, what we obtain is x2 immediately equals 0, and then if x2 equals 0, then this term goes away, and what we have is sine x1 also 0. And if sine x1 equals 0, so that means x1 must be an integral multiple of pi. And that produces a family of equilibrium points that are isolated. X equilibrium are 0, 0, plus minus pi, 0, plus minus 2 pi, 0, and so on. But of course, if you look at the actual physical system, even though here we have infinitely many, we seem to have infinitely many equilibrium points. For the physical system, there are actually two equilibrium points. One of them is the one where the mass is pointing down, the other is where the mass is pointing up. Okay, so namely 0, 0 and 0 pi. Excuse me, 0, 0 and pi 0. Okay. Now let's move on to another example. Which also an important example from the application world. It's phase-like loop. Here is the description of the system. A phase-like loop can be represented by the following block diagram. Okay, here we have the reference phase, or reference angle, and then it's compared to the actual phase, let's call it the output phase, output angle, theta O, and their difference is defined to be the error, E. That error is passed through this algebraic block, sine block, and it produces sine of E at its output, and that's fed to a block that can be represented by the linear time invariant system, for which the transfer function, suppose, is denoted by g of s. Okay? And what comes out, a scalar, is what we call the output of the system. Okay, wow. And then that output is fed back to the starting point to produce the error. Okay, so this here, this signal we can call the input to this linear block, G of s. Now, let A, B, C, the all matrices, be a minimum realization for this input-output plug G of S be a minimum of the scalar, because both the input and the output are scalars, strictly proper. Transfer function that appears in our block diagram as GS. Assume, okay, so we will list further conditions. Assume that all eigenvalues of A have strictly negative real parts. Okay. Therefore, we're talking about an exponentially stable case for this block. And suppose that the transfer function does not have a zero at the origin, so G0 is different than 0. And this input phase is a constant, it's not varying with respect to time. Or maybe it's varying, but its variation is so slow that for the sake of argument we can take it as constant. Okay? And theta I is constant. And finally, let Z be the state of the realization, A, B, C. Okay, so that's how we denote the state of the realization. The state of the realization. A, B, C. Now, this is the system, and those are the assumptions that are being satisfied. And for this scenario, we are asked the following. A, show that the closed-loop system can be represented by the state equation. Z dot equals AZ plus B sine of E, E being the error, and E dot equals minus CZ. I apologize, I've got an integrator block here. Okay, so here we have an integrator block. So to generate error, the output is not fed directly to the beginning, but we integrate the output and we feed that to the reference point. Okay, so basically we're talking about integral control here. Okay, equals minus CZ, and okay, so that's A. And in part B, find all including points of the system, of the closed-loop system. Okay, and in part C, show that when G of S is a first-order transfer function, of the following form: tau s plus 1, closed loop model coincides with the equation of the pendulum that we have just talked about. Coincides with the model of pendulum equation. Okay, now let's start from A. So z dot equals az plus bu, y equals cz. Okay, so this is the state space representation of the transfer function g of s. Okay, the output is y equals u, and since the g of s, that transfer function, has a realization a, b, c, therefore the relation between input and output can be put in this form, where z is the state of the system. This is a minimal realization. Okay, therefore it's both controllable and observable. And at this point, we don't make any assumptions on the order of the system. Okay, what we know is that y is a scalar, u is a scalar, but z could be a vector of any dimension for the part A. Anyway, so that's the g of s part. Then what we have is input to that block is coming from the error. It's not directly the error, but error passed through the sine function. Therefore, u equals sine of e. Okay. And what else? We have e equals this constant, the reference angle, minus the integral of the output. Okay. Integral of the output. Plus some initial condition of the output. But since we're going to differentiate this equation to obtain E dot, without also generality, we can take the initial condition for the integration to be 0. Okay. So this produces what? E dot equals, this is constant, therefore when you differentiate that, it disappears. Then we have integral, that's integral disappears, and we're left with minus y when you differentiate. Minus y. And since y is c of c, therefore we can write E dot to equal minus cz. Therefore, combining the last thing and the first thing that we have written down, we have the following model for the closed subsystem. Z dot equals az plus b instead of u, now we have sine e, and E dot equals minus cz. Now this is now in the form of x that equals f of x, where x is the overall state which we obtain by combining z and e, stacking them into a single vector, and then these two things put into a single vector make our f of x in that case. Okay, so that completes part A. Now let's move on to part B, where we asked to figure out the equilibrium points for this autonomous system x equals f of x. For that, what we will do, we will directly apply the definition of the equilibrium point. This is f of x. We equate that to 0, and from that we're gonna hopefully find the equilibrium points. This is our right hand side, and to find the equilibrium point, let's equate that to 0. 0 equals AZ plus B sine E. Okay, where this 0 is of dimension of this vector Z. At this point, we don't make any assumptions, so in general, it doesn't have to be a scalar, like Z. Then we have 0 equals minus CZ, where this 0 is a scalar because this is the output of the system, and output is scalar, minus CZ. Now, the first equation yields the following: Z equals minus A inverse B sine E. Okay. Now, how do we know that A inverse exists? Okay, we know it because we're given in the description of the problem that all the eigenvalues are with negative unit parts. So that means we have no eigenvalue at the origin. Okay. No eigenvalue at the origin means A is full rank. If it's full rank, it's invertible. Therefore, taking inverse is allowed. As for the second equation, or combining the second equation with the first, with this one that we have figured out, what we have is, so Z is this, so plug this Z into here, and what we have here is C A inverse B sine E equals 0. Okay. So this is what we obtain in Z at the equilibrium point, or at any possible equilibrium point. Then we take that Z and plug it in here, and we equate it to 0. Okay. So therefore, that's what should be satisfied. And then let's move on. Okay. So minus CSI minus A inverse B S equals 0 sine E equals 0. So what we did is we wrote or rewrote this equation in this funny form. Okay. If you plug in S equals 0, what you have is this term goes away, and what you're left with is C times minus A's inverse times B, and here we have another minus. For those two minuses will cancel out, and we have exactly this equation here. Okay. But the question is why have we complicated this simple equation in this form? Is because if you write this thing as in this form, we immediately recognize that this is no other than the transfer function, g of s. Okay. And then what we're talking about here is the value of the transfer function at the origin, s equals 0. And we know that we don't know exactly what that value is, but we know that because we're given in the problem description that that's different than 0. If that's different than 0, this equation is satisfied only for sine E equals 0. And that will give us what E should be at a possible equilibrium point. Okay. So from here, we write g of s at s equals 0 times sine E equals 0. And g of s at s equals 0 is non-zero, therefore sine E must equal 0. Okay. And that means E must be an integral multiple of pi radians. Okay, k equals 0 plus minus 1 plus minus 2 and so on. And from that E, what we have is Z equals, okay, this is what Z is at equilibrium point, and then at equilibrium point sine E equals 0, therefore automatically Z must be 0 at any equilibrium. Z equals minus A inverse B sine E. Sine E is 0, equilibrium, and that's 0. Therefore, ZE, the state, or the possible equilibrium points for the overall state of the closed loop system are as follows: 0, 0, 0, pi, 0, minus pi, and so on. 0, 2 pi, 0, minus 2 pi. Okay. Where this 0 is the 0 vector, and the dimensional vector is the dimension of the C here. Okay. And finally, in part C, we were asked to figure out or to show that the equation satisfied by error becomes the pendulum equation for a special transfer function, first order. Let's also show that, and we can move on to our next example. Okay. C. Now, for the transfer function g of s given to be tau s, 1 over tau s plus 1, this translates into, so this is in s domain, in time domain, s corresponds to differentiation, therefore what we have is tau y dot plus y equals the input. Okay. Then we have tau y dot plus y equals the input was coming from the sine block, and the input to that sine block was E, therefore U is sine E. Okay. And also from that feedback connection we know that E dot equals minus the output. Okay. And then if you replace this y with that E dot minus E dot, what we obtain is the following: tau E double dot plus E dot, right, okay, plus sine E equals 0. Okay, and this is the form that we study in for the pendulum equation. Now, our next example is coming from nonlinear circuit theory. Okay, it's a famous oscillator circuit due to, I believe, a scientist from the Netherlands, Van der Pol. So we'll be talking very briefly about the Van der Pol oscillator. Suppose we have this parallel RLC, parallel LC and nonlinear resistor circuit. Okay, we have a linear time varying capacitor connected in parallel with a linear time varying inductor, and those two are connected in parallel with nonlinear active component. Okay, C denote the capacitance, L the inductance, and the voltage current relationship for this nonlinear resistor is, suppose, of the following form. Okay. Well, this is the origin. So the shape tells us the following: for voltage and current, when they're small, here the slope is negative. Okay, so it behaves like a negative resistor in a sense. So what it means is it's an active component, that region. Well, it's an active component in general, but that region it produces, it pumps power to the rest of the circuit. So in a sense, it acts like a voltage source, okay, that drives the circuit. But as voltage or current increases further and further, it enters the passive region, okay, where the product, current voltage product is positive. So that means when it enters either this region or that region, it starts consuming energy, okay, dissipating energy from the circuit. Okay, so it's and that peculiar characteristic, the IV characteristic, generates what we call limit cycles, okay, in the overall circuit. This we will study later on when we talk about second order systems. Okay. For now, let's not worry about those. First, let's obtain the system description for this circuit. Okay. So let this be the capacitive current, let this be inductor current, and the current for the non-linear element is denoted by I. There's only one voltage because everything is parallel to one another, and that voltage is indicated by V. Now, starting from KCL, Kirchhoff's current law, we can claim that the sum of those three currents, IC, IL plus I, must be zero. And from that equation, hopefully, we will obtain the differential equation that's needed for the description of the system. Okay. So that means, so IC is, let's try to indicate everything in terms of the voltage. Okay. C d dt v. Okay. So that's CV dot, that's capacitive current, plus IL plus I equals 0. Okay, we didn't touch IL and I at this point. Let's differentiate it once again so that we have the derivative of IL. Why we want the derivative of IL? Because once we have the derivative, we can express it in terms of voltage. And that's pretty much what we want to do. We want to be able to express this equation only in terms of the voltage. Okay, so differentiate with respect to time once again. So what we have is d squared dt squared v. So we have v double dot plus d over dt il plus di dt. Okay, and that must equal to 0. And then let's rewrite certain terms. dt squared v plus, this is 1 over L times the voltage of the inductor. So 1 over LV, so that's also in terms of V. And finally, we can express this in terms of V by using this mapping. Okay, I equals HV plus partial derivative of H with respect to V, and then times derivative with respect to time, dt. So let's call this guy here H prime. Okay, prime indicates partial derivative, partial differentiation with respect to V. Okay. Now let's write what we have obtained in a cleaner form. So what we have is V double dot plus. So this is the equation that we obtain. What we do is we divide everything. This is equals 0. Divide everything to by C, and what we have is V double dot plus 1 over LC V plus this whole thing divided by C. Okay. So H prime V over C times V dot plus 1 over LC V. Okay, that equals 0. Now, for simplicity, let's do some normalization. Suppose that the LC product is unity and epsilon indicates 1 over C, the reciprocal of C. Okay, in that case, we can rewrite this equation as follows. V double dot plus epsilon H prime V dot plus V equals 0. So let's call this equation number 1. Okay. So that's That's the description of this nonlinear circuit. Now, for limit cycles, okay, so what we need is, or one way to obtain limit cycles in the circuit is, we need the waveform, we need a curve that describes the current voltage relationship for this nonlinear element as such that is a component that pumps power for small voltages and consumes power for large voltages. Okay? And one way to realize such a shape is through the following function. For h of v equals minus v plus 1/3 v cubed. For small v, we can ignore v cubed term, and what we have is minus v, that is a negative resistance type component. For further, as you increase voltage further and further, this term starts dominating. Okay, so we can forget about this for large voltages. And what we have is that polynomial increase. Okay, in the first and third quadrants. So for such h, the equation, the general equation that we obtain, and we call it equation 1, boils down to this, the famous van der Pol equation. Okay, it's a very simple nonlinear differential equation, but the behavior that it generates is quite rich and interesting. Okay, wonderful equation. It is v double dot plus epsilon. Now h prime v for this particular choice of h becomes v squared minus 1 v dot plus v equals 0. Okay, and epsilon here is something positive. Okay. Now, to understand very roughly what this thing does is, let's consider this term as constant. Okay, even if it's not, this v squared minus 1 term constant, and in that case this becomes a homogeneous second order linear differential equation. Okay, if this, for this is constant, and for v small, what happens is, here we have a negative term. Okay, and the roots of the characteristic polynomial in that case would produce positive eigenvalue, okay, a positive pole, and that means the resulting dynamics would be unstable. That is, things tend to blow up, increase further and further. But as things tend to blow up, increase, this guy now becomes larger and larger, and it will dominate 1, and this thing all of a sudden becomes positive. Okay. Now suppose that v is very large, and again, once again, consider that this term is constant. In that case, for v is very large, we have a second order homogeneous differential equation, linear, but this time all the coefficients are positive. So that means all the eigenvalues are with negative real parts, and everything is stable. Everything should converge to the origin. Okay. Therefore, for very small voltages, everything tends to move away from the origin toward infinity, but for large voltages, everything is trying to move toward the origin. Okay. And then what happens in between is something very interesting. What happens is, well, it's not obvious by looking at this equation, at least not obvious to me, that the voltage or the solutions display stable oscillations. Okay, they are not sinusoidal but periodic oscillations. Okay. So let's quickly talk about the including points for this system. Then we can end our lecture. So, to put this into x equals f of x form, we have to choose two states because it's It's a second order differential equation. Let's choose states as v and v dot. So let x1 be v and x2 be v dot. In that case, what we have is x1 dot equals x2 dot equals minus x1 plus epsilon 1 minus x1 squared x2. Okay, so that's our f of x. Equilibrium points. Okay. What we do is we equate f of x to 0. So 0 equals x2 means that at any possible equilibrium, x2 must be 0. And for the other guy, 0 equals minus x1 plus epsilon 1 minus x1 squared x2. Okay. Now at equilibrium, x2 equals 0. If x2 equals 0, then this term just goes away, and what we have is minus x1 equals 0, therefore x1 must also be 0. So therefore there's only one equilibrium point, and that's the origin. Hence, x equilibrium, the origin. Okay. Now if you start at the origin, you stay at the origin for all times, but the slightest disturbance, we'll see later on that, will push you away from the origin. Okay? And it doesn't push you away from the origin indefinitely. At some point, you converge to a stable periodic solution. Okay? So that's what happens if you start in the vicinity of the origin. And if you start very far away from the origin, again, this time you converge to the origin. Okay? You move toward the origin for a while, but you do not reach origin. What you do is you reach again that stable periodic solution. Okay? So it's a very interesting behavior. And if you want to see that behavior, if you want to get some visual understanding, we can easily simulate this differential equation in MATLAB. Okay? You can do that. If you don't have time, the files, necessary files, are on the web page. You can quickly take them and greatly simulate and also see the oscillations. And for your simulation, it would be a nice exercise to see how the behavior changes as you play with epsilon. What happens for epsilon very tiny? What happens when epsilon is very large, and so on. Okay. In our next lecture, we will start talking about second order systems.